Hello, discrete math fans. Let's talk about functions acting on sets. We usually think of functions as acting on elements of a set. Now we'll have them act on subsets of the domain and subsets of the codomain. Given a function f with domain x and codomain y, we can consider the set of images in y of all the elements in a subset of x, and the set of inverse images in x of all the elements in a subset of y. Let's make a definition. Suppose that f mapping from x to y is a function. We'll suppose a is a subset of x and c is a subset of y. Then f of a, that's f acting on a subset of x, is the set of all little y's in the codomain such that little y is equal to f of x for some x in a. And we can say that f inverse of c is equal to the set of all x in the domain such that f of x is an element of c. F of a is called the image of a. F inverse of c is called the inverse image of c. As an example, let's take this function f that maps from the set that contains 1, 2, 3, 4 into the set containing q, r, s, t, u, v. We'll define f of 1 to be r, f of 2 to be s, f of 3 to be u, f of 4 to be r. And you can see that with the arrow diagram. We're going to create a set A to be just the set containing 1 and 2, and we'll let C be the set containing q, r, s. So here's A, here's C, and we want to know what is f of A, what is f inverse of C. A is equal to the set containing 1 and 2. We know that f of 1 is r, f of 2 is s. Then f of a is the set containing r and s. That's the set that the elements of A get mapped to. So we've marked that in red, and you can see that the image of the elements 1 and 2 are the elements r and s. So we make a set out of those. That's the image of A. All right. Now we're going the other way. We're going to let C be the set containing q, r, and s. We know that f of 1 is equal to r, and that's in C. F of 2 is equal to s, that's also in C. And f of 4 is equal to r, which is in C. And so now the inverse image of C is the set containing 1, 2, and 4. It's the set of all things that the function maps to an element in C. So we look at these guys here, that's our set C, and see what elements map into that subset of the codomain. Let's do another example involving proofs. Let's let f mapping from x to y be a function, and then for all sets a and b, with a and b both being subsets of x, we'll prove or disprove f of a intersect b equals f of a intersect f of b. Now, it's actually pretty easy to see that this statement is false. As a counterexample, let's let x be the set containing 1 and 2. Let's let y be the set containing 3 and 4. And we'll create a function. We'll define f of 1 to be equal to 3 and f of 2 to also be equal to 3. Then, if we let a be the set containing the number 1 and b being the set containing the number 2, then a intersect b, obviously that's empty, and so that means f of a intersect b is empty. But f of a is f of the set containing 1, and that's going to be the set containing 3. F of b is f of the set containing 2, that's also the set containing 3. So f of a intersect f of b is equal to the set containing 3. So at this point, what we have is that f of a intersect b is the empty set, f of a intersect f of b is the set containing 3. Therefore, for this choice of f and for the sets a and b, we have that f of a intersect b is not equal to f of a intersect f of b. So we have produced a counterexample, and that means the given statement is false. Let's try this one. Prove or disprove. Again, we'll let f mapping from x to y be a function. For all sets C and D, with C a subset of y and D a subset of y, f inverse of C intersect D is a subset of f inverse of C intersect f inverse of D. All right, now this one is true, and we'll prove it with the element method. Let's let x be an element of f inverse of C intersect D. Okay, what does that mean? It means there's a y in C intersect D such that f of x is equal to y. That's just the definition of this inverse image. Now, y is an element of C intersect D. That tells us that y is in C and y is in D. Since y is an element of C, then we know that x is an element of f inverse of C. And in the same way, since y is in D, we know that y is an f inverse of D. And that means y is in both of those sets, f inverse of C intersect f inverse of D. And that's the end of the proof. We've chased the element from one side to the other, and that proves that we have a subset relationship. And as it turns out, you could try to see if it works the other way, and it probably does. Okay, that's all for now.